Hello, SP6GK here, and today I will show you how to simulate a multiple dielectric PCB with a microstrip structure on top. Why is this important in your design? And if you remember in previous video, the first video to be exact, I have explained to you using the TX line tool that the width of the PC of your trace and your height of the dielectric determines the impedance. Well, there are other factors, but let's say that this two that we can quite easily control as our variables. Well, it turns out that in a four-layer board, which is often used, for example, in a digital design, the layers in between are separated by prepreg, and this prepreg is quite thin. It's only 0.2 millimeters in this case. And what's more interesting even is that its dielectric constant is different than our core, so this FR4 material here. Well, there's also the copper layer in between. So if you wanted to implement the microstrip structure between these first three layers, you will find yourself in a situation where your dielectric is only 0.2 millimeters. And if you plug the numbers into a calculator, I will of course include the links in a video description, you will find that the width of a 50 ohm trace is only 0.34 millimeters. And this might be quite okay for layouts of a boards when you just need to deliver this 50 ohm transmission line from one point to the other. However, if you, for example, designing the microwave structures that use this microstrip technology, for example, to create low impedance points, you might find yourself that the widths are just not suitable for your design. For example, in the previous video, I have shown you the low pass filter that required a high impedance trace, and this trace became too narrow to implement. The white traces, of course, present lower impedance, and for higher dielectric, the taller dielectric, let's say, layer, they will be, of course, even wider, and for a lower dielectric, they will be more narrow. So you can see a problem here that on a four-layer board, implementing, for example, an inductor, so something that has high impedance, might become impossible because the trace will be too narrow. And how we can overcome this is that we could remove with some sort of mask or just omit the copper pore of this L2 layer and use the L3 as a ground plane and L1 as a signal layer. So how we go around to simulate this in a microwave office? Let's create a completely new project with a new schematic. I will call this the EM, maybe the 4 layer. This will be, let's start with a closed simulation first to see our concept of what we need to do. So similar to the first video, we will start with the M sub, but here we need to go for a 2-layer microstrip substrate definition. You can see it has much more parameters. So going for the 7628A PCB substrate or stackup layer defined by GLC PCB, I will go for a 4.4 of the electric constant for the prepreg and 4.6 for our core. We are sort of curious if this will impact our simulation or not, but we have a quite powerful tool to check this, so why not use it? Now, first, I will set the tangent loss to the same number that is quite typical for the FR4. This is not the point of our consideration here, but we'll leave it. The conductivity I will set for a 0, so assuming that this is some ideal material in this case, not really crucial here. And the height one is of course our prepreg, so this will be 0.2104 millimeters, while the core is much thicker of 1.065. Now the thickness is defined for the top layers because this is our signal layer. And of course, we also need to define the ratio of conductivity between the copper and the gold, which I've explained in the first video. And you can also use the TX line for this. Now, great. We will also want, of course, our transmission line. Transmission line on a two-layer substrate is defined as MM1 lin. And let's add some ports. Okay, we have our two ports. I will now, this is not exactly what I wanted to do. Let's just connect these elements. I will set some convenient lengths of 100 millimeters and the width of a trace to W0 at first. And press Ctrl E to put the equation, and let's put it W0 at, for example, 1 millimeter for now. Okay, so in case of a just single dielectric on two-layer board, we would use the TX line tool. Let's put the 4.5 because we don't know effectively what our dielectric constant is because we have two, right? So let's start with the height of the board. The height of the board, let's fire up the calculator, will be the sum of our prepreg and the core height. So this is 1.065 plus 0.2104. So 1.27. So effectively, this is a little bit shorter than the 1.6 millimeter two-layer board, where we would expect for usually something around 3 millimeters thickness of a 50 ohm trace. So our trace should be a little bit more narrow than 3 millimeters. So let's go back to the TX line tool and enter. I will copy the height here. Okay, let's not this way. We want to actually go for a 50 ohm impedance. Go this way. So yeah, it changed our width of a 2.49. Yeah, so this is quite what we predicted. Okay, let's put this W0 here. So this is our first guess. We don't know if this will work or no. That's why I will use this tuner tool on the W0 variable. Okay, our project doesn't have a specified simulation option, so I will go to the frequencies and start range will be, let's simulate between 0.1 gigahertz, 100 megahertz and 10 gigahertz with the 100 megahertz stop, maybe. That's 100 points. Okay, we can go with that for now. Great. Okay, I think we have everything set up for this closed form simulation. Let's create our first graphs. There are the graphs. Let's go for the rectangular graph and let's call it the 4 layers. Closed. Okay, we'll add, of course, 2 measurements of the S11. This is all correct. And of course, to S22. Sorry, S21. Okay, simulate. Yes, our simulation is correct, and you can see the return loss. There's of course some ripple coming from the quarter wavelength and the different ratios of it. Of course, we have some losses that are quite intrinsic, but the return loss is actually excellent. I would say it's well below minus 20 dB, so this is very small reflection. If you want to see this on a Smith chart, you can actually create a new graph. Let's go for a Smith chart and we'll call it the Smith 4 layers. And here it's actually, I think, quite simple because you don't have to remember about setting this dBs. Just from port 1 to 1 will be fine. Okay, I will need to hit the analyze button once again, and you can see that this is really a pointless example, because the match is very, very close. It's quite frequency. I would say it's practically frequency independent on the scale. Um, what you can also do, and this is quite useful, is you can choose beside the sweep, you can choose a single frequency. So let's say you are interested in what happens at 900 megahertz, and this is only a single layer, single point. So this is quite handy when you are dealing with a Smith charts. And if we fire up now our charts and hit the tune button, we can actually change the width of our 50 ohm trace, or what we want to be a 50 ohm trace. So I will change this, for example, to be maximum of 5 millimeters and 0.1. Okay, so let's check. You see, so for example, this is quite poor match, of course, and here is also a poor match. So you can see that there's a clear minimum to it, and you can find that this minimum is actually very close to the value that we've calculated of 2.4 millimeters, which basically shows us that this prepreg has very small impact according to this closed force simulation. So in order to be more confident in our assumptions and to be closer to a confirmation that this prepreg in our stackup doesn't have much of an impact, let's copy this simulation and we will change it to electromagnetic simulation of this multiple dielectrics. So this will be now our EM simulation. I will disable this tuning and I will also close these graphs. Great. Okay, so after copying the schematic and changing the name, we should prepare it for the electromagnetic simulation. First, of course, click on this single element of Microstrip, align and enable the extraction, hit OK. Now we'll go for a tools, for the scripts, the EM, and create stackup, and go for a grid of, let's say, 0.1 millimeter. Now this will be, actually I'm not sure why it puts 1 here. Let's put 0.1 once more, maybe that's a bug. And let's prepare the stackup. Double click on stackup. Here is actually quite a lot of steps that we need to put manually here because we have this double dielectric layers. So let's add 2 dielectrics. First, let's put the preset FR4, but I will change it to the top because this is our prepreg actually. And let's put 4.4 and 0.02 of our tangent loss. Hit OK. It's a nice feature that you can change this color and the pattern here, so I'll try to differentiate it a little bit. This will be okay. Now let's put the actual FR4, okay, and we will set it to 4.6. Actually, I've just noticed that you can put this 7628 here. I'm not sure if I did that previously or this is a default, but it's a cool feature if it's default. Okay, 4.6 it was, and the same tangent loss. Great. Now we also have 2 conductors. So let's put a copper, and this is a copper top. This will be our thicker layer. And we also have an inner copper. So let's put a copper inner. Okay, so this is everything that we need from this tab. Let's go to the next one. And this view is basically our, let's say, stack up, right? So we will see, as we add materials, we will see more and more. So first is air, and I will put, let's say, like 200 millimeters, so like 20 centimeters away from the board. It includes our simulation above it, let's say. And, you know, if you have, for example, some sort of metal enclosure and so on, you can add it later on to these materials and include a much smaller, for example, air thickness. We'll add another layer. It will be the layer 2. Um, and this will be our top layer, and the material definition is of course our top. Sorry, I should put the thickness here. So the thickness of our prepreg is 0.21. Now the scale, I will not care that much about the scale, right? Because you will notice that these blocks will be uh, the same height, even if I change it to 1.065. And this is our FR4 core. So you can see it changed the color. It has 4.6 dielectric constant, and it has 4.4 and 0.2 for a prepreg. I will not simulate the layer in between. It's very thin, and in theory it should be, year one, I think, right? Because there's nothing, but if you put it actually so close, I think just these two should stick pretty close to each other. But this goes more for a mechanical, let's say, inspection of this PCB, which I'm not really able to check here. Uh, Let's go to the materials, because this is something that we have to set. We have our perfect conductor. I will add two traces. The trace 2 will be our prepreg, because it's, let's say, this inner two layer, and it's 0.0152. This is fine, and it's copper inner. Now the next one is trace 1, so this is our top, and it's much thicker, of 0.035 millimeters, or 35 micron. Good. Now the EM mapping, the layer should be 2, right? Yeah, it did appear here. So this is our conductor layer 2. Trace 2. Sorry, trace 1. Trace 1 is our top. Yeah, so we have a conductor of thickness 0.0. If we hover over this, it's 0.035, so this is okay. Sorry for the confusion. And trace 1 is our top. Maybe the naming convention I should have chosen for something better, but either way, if we press here, yes, it's set correctly. Now the line type. For the line type, we set, of course, the default trace 1 and EM layer 2. So this does appear here, and I will also select the specify grounds, because for the lower ground, so this trace, this ground plane here, we will select, sorry, it was which layer? 4, right? And I think we have everything. We have the bottom layer, the lowest one. This is the 4. It doesn't actually show us here when I hover over it. This is quite unfortunate. And the lower ground is of course copper inner, because it has different thickness. It's different thickness of the 0.015. Then we have the third layer from the bottom. This is the dielectric, this is the core, this is the prepreg, and then let's check once again, we have thickness of this layer. So this is great. I will set the top boundary. This is our first layer. I think we can set it as it's, right? It will not change this much here. Okay, great. So this should be everything that we were to set here. Let's hit OK, and let's add extraction. With the Axiom simulator, this is our line. Let's try to show the grid. Let's wait a little bit for it to finish mapping this grid. Yeah, so this is a fine mesh here, good enough for what we are doing. I will save it just in case. Great, so now what is left to do is add graphs. So I will add new rectangular graph and call it 4 layers. I will add 2 measurements of S21 from the EM extract. This is set correctly. And to S11 for our reflection. I think we'll have different colors than the previous time, but that's fine. What I will also do is I will change the measurements for the S11 to be on the right. and I will add appropriate levels, so labels. Sorry. So on the left we will have the insertion loss, of course, expressed in dB. Okay, and on the right we have S11 expressed also in dB. Fine. And now let's hit simulate. Now this might take some time, so I will just speed it up because we have two dielectrics, and the simulator actually has much more many layers to simulate. So let's speed it up, and I will see you when we get some results. Okay, we are done. It took 1 minute and 5 seconds. So certainly much more than our previous simulation of electromagnetic low-pass filter. And you can see that it's not as pretty above 6 gigahertz, but below that frequency it has a very good return loss. This is also of course excellent return loss, but you can see some effects here. And of course, this is especially above 5 gigahertz. This is above what you would expect from a FR4 substrate. Like, it's not very suitable for this kind of work, but the simulation tells us that yes, our width of the trace and the two dielectric layers that we have in between create a very fine match for a 50 ohms. You can of course play with this width and adjust it for the best return loss, but for me this is a nice confirmation with this powerful tool that yes, indeed, you can use the top layer as a signal, the prepreg and the core as your combined, let's say, dielectric. You can omit the pore on the inner layer, the first inner layer, and use the second inner layer as a ground plane. So concluding, combination of these layers gave us a stack up that is quite useful for microstrip structures, because the width of a 50 ohm trace is quite reasonable, and the width of a high impedance traces will be probably possible to manufacture. Actually, it's very close to what we've done before with the 1.6 millimeter high two-layer board, but the 50 ohm trace is 0.6 millimeter thinner. So yeah, I think most of the structures with the high impedance, like the low pass filters, will work just fine, and the other structures should also be possible. And that's all on a very cheap PCB, where you can also implement more complex digital circuits that might require you to, change between first inner layer and the second inner layer and so on. So part of the PCB can be digital, part can be RF, and this is something that I want to implement in one of my projects. And actually one of the videos will show you a physical measurement of a board, evaluation board, on which I have a microstrip filters that are implemented on those top layers on a 4-layer board, exactly on this substrate. Anyway, thanks very much for watching, and I hope that you will see another videos. In the next video, I will probably show you how to work with the X parameters in AWR Designer, so that you can, for example, import measurement from your VNA into the block and use matching networks, for example, to observe the effects on the port parameters. But that will be in the future. Anyway, thanks very much for watching.